Welcome grade 12s to STEM in Action's Boost series. I'm V Guyan and today we're going to look at electric circuits. Some pre-knowledge you should know from grade 10 and 11. Firstly, we know about electrical current, which is the rate of flow of charge. We know that we normally use conventional current, which flows from positive to negative, but in actual fact the electrons flow from negative to positive. Remember that we use an ammeter to measure electrical current. We also know about potential difference or voltage, which is the work done per unit charge in moving it between 2 points in a circuit. We use a voltmeter to measure potential difference. Then we get resistance. Resistance is the opposition to flow of charge. We also learnt about series and parallel circuits in grade 10 and 11, and we'll recap on those today. We also learnt about Ohm's Law in grade 11, and finally we learnt about the power of electrical components in a circuit. We'll recap on both of those today. So firstly, a series circuit. What do we know about a basic series circuit? If we have a look at the diagram on the slide, we can see that we have 3 resistors in series: resistor 1, resistor 2, and resistor 3. And we have various voltmeters and ammeters in the circuit. What do we know about the resistances? We know that the total resistance in the circuit will be a sum of the individual resistances for a series circuit. Current in a series circuit is the same everywhere in the circuit. So the reading we get on A1, A2, A3, and A total will all be the same. Notice over here I've said I total, I1, I2, and I3. I is the symbol for current, where A is the symbol for an ammeter, or for the unit of current, which is amps. The voltage in a series circuit is shared between the resistors. So our V total that we get is equal to V1, the voltage across resistor 1, V2, the voltage across resistor 2, and V3, the voltage across resistor 3. In a parallel circuit, to calculate the total resistance, we need to say 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. You will then get an answer for that, which is, say for example, X, and then we must invert that to get R total. Don't forget to invert to get your R total. Current is split in a parallel circuit. So that means current comes from the battery, so you've got your electrons flowing out and they get to this point over here and they can choose where to go. So some of the charges will flow through resistor 1, some will flow through resistor 2, and some will flow through resistor 3. And so if we take those 3 current readings, the reading on A1, A2, and A3, they will add up to the total current, which all goes back through the battery. And so over here we have I total is equal to I1 plus I2 plus I3. Finally, the voltage in a parallel circuit is the same everywhere. And so V total is going to equal to V1, which is also equal to V2, which is also equal to V3. Let's recap Ohm's law. Ohm's law says the potential difference across a conductor is directly proportional to the current in the conductor at a constant temperature. So if we had to plot Ohm's law, we would get a nice straight line graph here when we're plotting voltage versus current, and the slope or the gradient of the graph is our resistance. We also get non-ohmic resistors. Those are ones that don't obey Ohm's law. In those cases we get a curved graph which shows us that Ohm's law is not obeyed. We learnt about power in grade 11, and we learnt that power is the rate at which work is done. You also learnt about power in work, energy, and power in mechanics. This power is slightly different because we're looking at the power in a circuit, but you'll notice that your definition is the same. So what equations do we have for power? Well, power is equal to work, the rate at which work is done, so it's work over time. But we can also look at it in terms of current and voltage and resistance. And so we get power is equal to I squared R, or power is equal to VI, or power is equal to V squared over R. All of these formulas are found on your data sheet. Lastly, in grade 11, you also learned about the power in terms of kilowatts per hour. And so 1 kilowatt per hour is 1 kilowatt of electricity used for 1 hour. And they use that unit to calculate the cost of electricity in households. What is new to grade 12 is EMF and internal resistance. EMF, or electromotive force, is the maximum energy provided by a battery per coulomb charge passing through it. EMF is equal to IR plus R, where I is our current, capital R is our resistance of our load, of our external circuit, and little r is our internal resistance. Remember that R, sometimes they might call it your external resistance, or they'll call it your load. They're talking about the same thing, and it is the resistance in the circuit. Your internal resistance, your little r, that is the resistance experienced within a battery. So within moving the charges through a battery, there is a little bit of resistance. That is called the internal resistance. Right, so if we have a look a little bit more at internal resistance, so we know that EMF is equal to IR plus R. If we multiply that out, we get that EMF is equal to IR plus I little r. We know that I capital R, current times resistance, is equal to voltage. It's capital R, we're talking about the external resistance or the resistance of the load, and so we get V load. If we're talking about I times little r, we're still going to get a voltage, but now we're looking at internal voltage. So we can see that our EMF is equal to our V load plus our V internal. So we know that V internal is equal to IR, and so we can change this formula just slightly to be E is equal to V load plus IR. If we have a look at our graph that we get from doing our internal resistance experiment, we can see that on our y-axis we have V load, our voltage, and on our x-axis we have our current. So we can take this formula that we've got for EMF and rearrange it to get it in the form y equals mx plus c, to get the equation of the straight line given in the graph. So the first thing I'm going to do is I'm going to make V load the subject of a formula, because that is what is on my y-axis. I also notice that on my x-axis is the current, so in the position for x I need to have my I, my current. So I can rearrange the equation and I get V load is equal to minus R times I plus EMF. Essentially what I've done is I've taken this IR over this side, and so it became negative IR, and I just swapped the I and the R. 2 times 3, 3 times 2, same thing. So R times I, or I times R, is the same. Why have I done that? Well, so that I can link all of this together. We can see that V load is on our y-axis. Our negative R is now our gradient, because I is our x, and we also then get that EMF is our y-intercept. So if we go over to the graph and have a look, we know that the slope of the graph is equal to negative R. Remember, this little r is the internal resistance, so if we can find the slope, we can make it equal to negative R, and then we can solve for internal resistance. Remember, we don't want negative R, we want to know what is the internal resistance, so we'd have to solve that little equation. And then we also know that over here, the y-intercept, that is our EMF. Right, so let's have a look at a combination of a series and a parallel circuit. We can see here we've got 4 resistors. This one is in series, all the current has to go through it. Then we get here where the current's got a choice, so we get a parallel combination. In the first branch though, we have 2 resistors in series, and those 2 together are in parallel to R4, and the current then joins back up and goes back into the battery. So we've got a resistor in series to a parallel combination, then we've got a series combination in parallel with another resistor. So it's quite a combination there. Let's have a look at what we can tell about our voltages and currents in this circuit. So firstly, the switch is open, then that means that V total is currently reading the EMF. So if there's no current flowing and we put a voltmeter across our battery, we will be reading the EMF. If we then close the circuit, our EMF is now equal to our V total plus our V internal. So V total is no longer reading the EMF, it's now reading the V load, or the voltage that's available to the rest of the circuit. If we then have a look at our other voltmeters and we look at our parallel combination, we can see that V2 plus 3 are going to be equal to V4. Remember that in a parallel combination, the voltage across each branch is equal. But then within one of our branches, we have a series combination, and we know that for series resistors, the voltage is shared. And so that is why V4 will be equal to the sum of the voltages across V2 and V3. Finally, if we have a look at resistor 1 there, we know that resistor 1 is in series to our parallel combination. And so resistor 1 shares the total voltage with the parallel combination. And so total voltage will equal to V1 plus V4. Why am I using V4? Because V4 represents a whole branch of the parallel combination. We could substitute in then that V4 is equal to V2 plus V3, but we're just going to keep it simpler. So remember that we've got to use a combination of our rules when it comes to voltages. And so you've got to keep looking at, is it in series or is it in parallel? Right, let's have a look at our current readings. If we have a look at our ammeter, a total up at the top, that is reading all the current that goes through the battery, but it's going to be equal to A1 because A1 is in series with the battery, and so all the current must also flow through resistor 1. However, when we get to the parallel combination, we know that the current must split. And so we can then see that A1 or A total will be shared between the branches, between A2 and A3. So A1 would be equal to A2 plus A3. Notice that the current through resistor 2 and resistor 3 is represented by A2. The current that flows through resistor 2 is also going to flow through resistor 3 because they are in series. Let's have a look at an application question. We'll have a look at the November 2019 Paper 1, Question 8. Question 8 says, in the circuit diagram below, resistor R with a resistance of 5.6 ohms is connected together with a switch, an ammeter, and a high resistance voltmeter to a battery with an unknown internal resistance R. The resistance of the connecting wires and the ammeter may be ignored. The graph below shows the potential difference across the terminals of the battery as a function of time. At time t1, switch S is closed. Right, so from this graph, we can immediately see that from time 0 to time 1, the switch was open. So our voltmeter is across the battery. If the switch is open, it's reading the EMF. And when the switch is closed, it's now reading V load. Right, question 8.1 says define the term EMF of a battery. So we did this earlier in the slide. We said that the EMF is the maximum energy provided per unit charge by a battery to all the charges passing through it. So let's write that down. EMF is the maximum energy provided by a battery per unit charge passing through it. Right, question 8.2 then says, write down the value of the EMF of the battery. We already discussed this. We said from time 0 to time 1, the switch was open, and so the voltmeter was reading the EMF, and so the EMF there is 13 volts. Right, question 8.3 says, when switch S is closed, calculate 8.3.1, the current through resistor R. And so if we're looking at the circuit, there is only one resistor, and so when we talk about V load or R load, we're talking about that resistor. So over here we've got our V load, which is then the voltage across that resistor. So we've got the voltage, we've also got the resistance there, and so we can use Ohm's law to solve that question. Remember, Ohm's law is given on our data sheet there. R is equal to V over I. And so we can substitute in the values that we know. 5,6 is equal to the voltage across that resistor is 10,5 over the current. And so current comes here. It's equal to 10,5 over 5,6. And so 10.5 divided by 5.6, we get a current of 1,875, which we can round off to 1,88 amps. Then 8.3.2 asks us to calculate the power dissipated in resistor R. And so we're going to have a look again at our data sheet. We've got our current, we've got our resistance, and we've got our voltage for resistor R. So we can choose pretty much any one of these formulas. I'm going to use P equals VI, but any of them would work. You would just substitute in different values. So P equals VI. V, remember we said, was 10,5. I, we've just calculated as 1,88. And so we put that into our calculator. And we get 19,74 watts. Remember, the unit for power is watts. Then 8.3.3, we are looking for the internal resistance of the battery. So we know, and we can also find it again on our data sheet, EMF is equal to IR plus R. Alright, so we're going to say EMF is equal to IR plus R. The EMF, remember we calculated there at the top, was 13 volts. The current, right, the current that's going through resistor R is the same current in the whole circuit because it's a series circuit. So we've got 1,88. R, our resistance of our load, is our 5,6. And we are looking for our internal resistance. So here we're going to solve this equation. We're going to say 13 divided by 1.88. And we're going to get 6,914. And I'm going to keep the rest of that answer there on my calculator. So I'm not going to round it off. So I put the dots in to show that I'm keeping the rest of the answer in the calculator. 5,6 plus R is now left on this side. So what do we need to do to get R by itself? We need to take that answer and subtract 5,6. So there I've still got the answer on my calculator. I can simply say minus 5.6. And we get R to be equal to 1,314. So 1,31 ohms. Right, let's have a look at question 8.4 from November 2019. This question says two identical resistors, each with resistance X, are now connected in the same circuit with switch S closed as shown below. The ammeter reading now increases to 4 amps. 8.4.1. How would the voltmeter reading change? Choose from increases, decreases, or remains the same. Give a reason for your answer by referring to V internal resistance. Okay, so if our ammeter is increasing, that means that our VIR, remember that V internal is equal to IR. And so if our current increases, our resistance doesn't change, the resistance of a battery is set, and so this increases, so our V internal increases, and we also know that V load plus V internal is equal to our EMF. If this is becoming bigger, V load must be becoming smaller because EMF is a constant. And so remember that our voltmeter, when the switch is closed, it is reading our V load. And so what happens? The V load decreases, and give a reason by referring to V internal resistance will increase. Okay. Sorry, that is 8.4.1. 8.4.2 then asks us to calculate the resistance of X. So what we're first going to do now is we're going to find our total resistance of our circuit as it is now. So because we know EMF is equal to I R plus R, we can go ahead and we can say, well, EMF was 13 volts for the circuit. Our current, they told us here in the question, it's increased to 4. Our external, that is what we're looking for. Our internal resistance of our battery, that hasn't changed. And we found that was 1,31. And so now we've just got to solve for our external. And so we're going to say 13 divided by 4 equals 3,25 is equal to R plus 1,31. And so R is going to equal 3,25 minus 1.31. And so we get 1,94. So we get that 1,94 ohms is the resistance of our external circuit or our load. But we're not done yet because we need to calculate X. And so we need to do a little bit more calculating. We know that these two are in series. And so to calculate their total resistance, we would just add them. So those two are going to be 2X. Over here, we can just add that. So the resistance in that branch is 2X. The resistance in this branch is 5,6. And because they're parallel branches, how do we calculate R total? It's 1 over R total equals 1 over branch 1, which is this one here. So let's first put in 1 over R1 plus 1 over R2. First put in our formula, and then we're going to go and sub in R1 is our 5,6 plus R2 is our 2X that we're trying to solve for. We know R total from what we calculated there is 1,94. And now we need to solve this equation. So first things first, I'm going to take this fraction over. So I'm going to have I'm going to write a fraction 1 over 1,94 minus 1 over 5,6. And we get, let's keep it in fraction form actually for now, 915 over 2716 is equal to 1 over 2x. When we have one fraction on each side of an equation, we can actually just invert both equations to make our life simpler. So it would be 2716 over 915 is equal to 2x over 1. And so this side then is just 2x. And so we can then say, well, we've got to take this answer, 2716 over 915, and then we've got to divide it by 2 to get x alone. So divided by 2, and we get x is equal to, now we don't want it as a fraction, we want it as a decimal, 1,48 ohms. Notice here you might have slightly different answers or numbers in your fraction depending on how you rounded off this previous answer, and even how R internal could affect, but you should get an answer around 1,48 ohms. That brings us to the end of question 8 from November 2019, and also to the end of our episode on electric circuits. We look forward to seeing you in our next episode.